We are going right down, way down, to the microscopic level.
To the front lines of an invisible war.
Exactly. Because I want to start with a really bold claim, maybe one of the wildest in all of biology. A war has been raging on this planet for billions of years, right under our noses. And it kills trillions of entities every single day. And the thing doing most of the killing is the single deadliest being on Earth.
That is the ultimate high-stakes hook, and the amazing thing is it's completely accurate. We're talking about death on a scale that is genuinely difficult to even visualize.
Right.
It's this vast, constant biological conflict that it utterly shapes the entire ecosystem of the planet.
Okay, so let's unpack this right away. My mind immediately goes to, the big stuff. Supervolcanoes, black holes. Maybe terrible reality television.
Yep.
If something is responsible for the majority of death on Earth, we need to know what this cosmic killer is. What are we talking about?
Well, the killer is microscopic. It's completely impossible to see without some serious magnification, and it looks like a terrifyingly beautiful creation born from fusing a robot and a spider.
Okay.
We're talking about the bacteriophage, or just phage for short.
A phage. So the idea that this tiny, insignificant-looking thing, this thing that looked like a miniature lunar landing module is the planet's ultimate mass murderer is, honestly, it's hilarious.
It is.
You're telling me that while we're all busy worrying about threats we can see, the actual undisputed champion of destruction is something that commits, and I'm quoting here, genocide for breakfast.
That is the profound contradiction, yes. It is the deadliest entity on the planet, wipes out massive populations daily, yet you, our listener, are completely and totally safe.
How does that work?
Well, that's the critical distinction we have to make right away. Phages only kill bacteria. They are precision, specialized predators. They hunt in the microbial world, and they don't care about us at all.
So for all of human history, we've been preoccupied with lions and bears and the things with teeth.
Right.
And we completely missed that the bacterial equivalent of an invisible cruise missile is wiping out populations a billion times over every minute. But okay, what makes this ancient war suddenly relevant to us? Why are we doing a whole deep dive on the planet's most prolific serial killer?
Because we're not just spectators anymore. This is really the mission for today's deep dive. We are examining this killer because the era of our own superweapon?
Antibiotics.
Antibiotics, yes. That era is definitively drawing to a close. For about 100 years, we thought we had mastered the microbial world, but we're losing control. We're losing it fast.
We got cocky. We messed up our one great advantage.
Exactly. Our chemical weapons are failing. So to survive this looming global crisis of antibiotic resistance, we desperately need a new, smarter ally in this ancient war.
And ironically,
yeah,
that ally is the deadliest thing on the planet.
A specialized virus that we now hope to deploy inside ourselves.
And here's where it gets really interesting, isn't it? We're looking at deploying the world's most effective killer into human bodies to solve a problem that we created.
It is the ultimate biological Hail Mary.
It really is. Okay, let's start by getting to know this paradoxical creature. What anatomically actually is a phage?
Well, phages are a type of virus, so they occupy that really fascinating gray area of existence. They're not quite alive, but they're not quite dead either.
Right, they're sort of these inert machines until they find a target.
Precisely. They're essentially just complex packages of genetic material, DNA or RNA, that's all wrapped up in a protective protein hull. They can't make their own energy. They can't reproduce on their own. They're purely parasitic machines.
And structurally, they look completely engineered. That's what gets me. They don't look like they evolved. They look like they were designed in a lab somewhere. Our sources all emphasize you really need a visual to understand how bizarre they are.
Oh, they're magnificent in their structure. They have what's called a head, which is basically the palade bay. This head is often an icosahedron.
That's a 20-faced, 30-edged shape, like a weird, super complex die.
Exactly. It's a perfect, stable little container that nature designed for maximum protection of, the sensitive genetic blueprint it's carrying inside.
So it's nature's super tough safe, and it's optimized for holding the deadly software. And that head sits on the part that I think is the most visually captivating, the tail structure.
The tail is the delivery system. It's this long, hollow tube, and it's often contractile, which means it can squeeze.
Okay.
And it's surrounded by a sheath. And at the very bottom, it has a base plate with multiple leg-like fibers sticking out.
Right, the lunar lander feet.
When you see a diagram, it looks exactly like a lunar lander that has just touched down on some alien surface. Those fibers are the anchors, the tail is the syringe, and the head. The head is the deadly package.
It's just entirely functional. It's built for efficiency and precision, nothing else. It doesn't waste any energy being anything other than a minimalist killing machine. And speaking of which, let's talk about their scale, because just saying they're everywhere doesn't do it justice.
The scale is what truly differentiates phages from everything else. The numbers are just staggering. They're estimated to be over 10 to the power of 31 phages on Earth.
Okay, so that's a 1 with 31 zeros after it. That number is meaningless to me. Put that in perspective.
Okay. There are more phages on this planet than every other organism combined.
Wait, what?
Every bacterium, every tree, every insect, every fish, every human, put them all together in a pile, and the phages still outnumber them by a landslide.
That is an astronomical number. We're not talking about just a few million here or there.
Right.
We are talking about a fundamental, foundational layer of biology that just completely dwarfs everything else.
And we're interacting with them constantly. It's estimated that if you took all the phages on Earth and you lined them up end to end, that line would stretch for 150 million light years.
That's just... No. That can't be right.
It is. They're in the air we breathe, the food we eat, the water we drink. There are billions of them on your hands right now, circulating in your intestines as part of your microbiome, and yes, clinging harmlessly to your eyelids.
So we host a microscopic, lethal superpower that just completely ignores us.
Exactly. And their ability to ignore us brings us back to their core genius. Extreme specialization. That is the safety valve in this entire terrifying system.
They're the ultimate snipers.
Precisely. Unlike a lot of viruses that are generalists or that can jump between species, which is, where our whole concern about pandemics comes from, phages are hyper-specialized.
So they need a host to survive and reproduce, and they're just incredibly picky about who that host is.
Extremely picky. They often target only one specific species of bacteria, or sometimes even just one specific strain of that species. They don't do collateral damage. They are all about precision destruction.
I love the analogy one of our sources used. A phage is like a cruise missile that only hunts and kills members of one very unlucky family.
That is the perfect way to put it. The whole mechanism hinges on molecular recognition.
Let's get into that. Let's detail that recognition and then the attack, because the killing mechanism is just brutally efficient. Walk us through that 5-step sequence from first contact to the final messy explosion.
It's a beautifully choreographed sequence of biological mechanics, and it's all over in just a matter of minutes. Step 1 is adsorption or connection.
The landing.
The landing, exactly. The phage, using those leg-like fibers, is basically just bumping around. Those fibers are keyed to recognize very specific protein or sugar receptors on the surface of a bacterium.
So it's a lock and key thing.
A perfect lock and key mechanism. If the surface isn't the right bacteria, the phage can't connect. It'll just drift away harmlessly.
So that initial handshake is the key to both their efficiency and their safety for us. Okay, so once it's locked on, the machinery takes over.
Step 2 is puncture. Once it's firmly attached, the tail sheath contracts violently. It's a really powerful motion. And that forces the inner tube, the syringe part, to puncture the tough outer armor of the bacterium, its cell wall.
So it's like a biological power drill.
It's an enzymatic and mechanical breach. It's designed to defeat one of the toughest structures in nature.
Now the payload is ready for delivery.
Step 3. Injection. The phage itself actually stays outside, like a spent shell casing, and it squeezes out its entire genetic payload, its DNA or RNA, straight into the bacterial cytoplasm.
And that's it. The warhead is delivered. The phage's body is just discarded.
Its mission is complete.
And the bacteria, completely unaware that it's just been handed its own death warrant, just starts following these new instructions.
Which leads to step 4, takeover and replication. And this is the definition of a biological hijacking. The phage DNA that was just injected completely overrides the bacteria's operating system.
It's a hostile takeover.
The bacterium is forced to stop all of its own life functions. No more eating, no more dividing. Instead, it becomes a literal factory manufacturing hundreds of tiny component parts to build brand new phages. Heads, tails, fibers, all of it.
It's a suicide factory. The bacteria is literally building the weapons that are about to kill it. And this just keeps going until the cell is, just bursting at the seams with baby viruses?
The cell is under immense hydrostatic pressure, which brings us to the very dramatic final step, lysis and release.
The big boom.
The big boom. The newly assembled phages inside start producing an enzyme called endolysin. This is the demolition charge. It chews a hole in the bacterial cell wall from the inside out.
And the pressure does the rest.
Exactly. When the wall's integrity fails, that immense pressure causes the bacteria to violently rupture. Or, as the source material so colorfully put it, it sort of vomits out all of its insides and dies.
Wow.
And this releases anywhere from 50 to 200 new fully formed phages, which immediately go out and seek new victims to restart the whole cycle.
That is just a phenomenal feedback loop of destruction, and we need to anchor this in a real data point just to emphasize the scale of this constant war.
Oh.
Our sources say up to 40% of all bacteria in the world's oceans are killed by phages.
Every single day.
Every day.
That's not just a statistic. It's an ecosystem regulator. If you suddenly removed all the phages, the bacterial population would just explode. It would consume vast resources, and life as we know it would fundamentally change.
So phages are the deadliest things on the planet, but they're also essential to keeping the planet in balance.
It's the ultimate deadly paradox.
It really is. Okay, so these phages are necessary killers that maintain the balance of the whole planet. But if they're doing such a great job, why did we, the supposedly smart humans, spend the last century trying to kill bacteria with chemicals instead?
And that's the perfect transition. We, the second deadliest beings on Earth, have only started looking at phages in earnest because, well, as the source says, we screwed up. We found a shortcut and we got complacent.
We really have to remember how terrified humans were just a little over a century ago. Before 1928, bacteria were the true monsters. A simple paper cut, a persistent cough, a routine infection after childbirth.
It could be a guaranteed, horrific death sentence. Bacteria were our natural predators. We lived in constant biological fear.
And then came the breakthrough. About 100 years ago, the discovery of antibiotics.
Mostly by accident, researchers found that certain fungi produced compounds that, well, they killed bacteria.
We had found our chemical superweapon, and the effect was just. It was revolutionary. It completely altered the risk landscape of human existence. Suddenly, pneumonia wasn't a death sentence anymore. It was an inconvenience.
We felt like we were masters of the domain.
For sure.
And the source material captures this shift perfectly. Antibiotics were so unbelievably effective that we just stopped seeing bacteria as these existential threats. The infections that used to kill us became the exception, reserved mostly for the very old, the very young, or the immunocompromised. We had banished the monster.
And right there is the core of how we screwed up. We let our guard down completely. We had this amazing superweapon, but we treated it like a cheap, disposable tool. We used antibiotics for everything. For viral infections where they did nothing, we pumped them into agriculture to promote livestock growth, and crucially, we failed to teach patients about finishing their courses of treatment.
We just completely failed to appreciate the power of evolution. I mean, bacteria are fast reproducing, highly adaptable organisms. Every single time we flooded our system with an antibiotic, we were applying massive evolutionary pressure.
We were creating a filter.
A perfect filter. Every time a bacterium got hit by the chemical, the few that had just a slight random mutation that gave them some protection, they survived.
It's Darwinism on hyperspeed, accelerated by human recklessness.
Exactly. We weren't just killing bacteria, we were actively selecting for resistance. And over time, that slight immunity became powerful resistance, and that resulted in the creation of superbugs.
Contrast the old superweapon with this new tool.
Oh, the difference is profound. It's the core of why phage therapy is so much better. Antibiotics are the definition of carpet bombing. When you take a broad-spectrum antibiotic, it floods your entire system. It kills the target pathogen, sure, but it also indiscriminately wipes out all the essential, beneficial bacteria, the good guys that live in your gut.
And that collateral damage leads to all kinds of serious secondary issues. Digestive problems, you're more susceptible to fungal infections, and you actually create an environment where resistant strains can flourish because all their competition is gone.
Phages are the complete opposite. They are the definition of guided missiles. We select a specific phage, or maybe a cocktail of a few of them, that is keyed only to the exact strain of bacteria causing the infection.
So they go in.
They enter the body, they seek out only their target, and they leave every other cell, including your entire crucial gut microbiome, completely untouched. It's precision-guided destruction without any of the ecological fallout.
This sounds ideal. It almost sounds too good to be true. But we have to address the evolutionary reality. Bacteria developed resistance to our best chemical weapons in less than 100 years. If we start relying on phages, Won't resistance just develop again just as quickly?
That is absolutely the right question to ask. But it relies on a flawed comparison. Antibiotics are fixed, static chemical
Oh,
compounds.
right. They don't change.
Phages are semi-living entities that replicate and, crucially, they evolve. This arms race, this war between phages and bacteria has been going on for billions of years, and the phages are extremely good at it.
They're fighting on their home turf, and they have a massive evolutionary head start.
Precisely. If a bacterium develops a new defense, say it changes its cell surface receptor so the phage can't grab on, that doesn't defeat the phage forever. It only defeats that specific variant of the phage.
Okay.
Within a few days, a new phage variant will arise that has mutated to recognize the new receptor. It bypasses the defense. This makes phages smart weapons that are constantly getting better at killing. They adapt to the defense in real time.
And this rapid evolutionary feedback loop, this leads directly to what our source material identifies as the most brilliant and surprising finding from the research, the catch-22 strategy.
This is truly biological brilliance.
So how do we use the bacterium's own need for defense against it?
It's all rooted in the concept of metabolic cost. Defense is expensive for a bacterium. Maintaining resistance to antibiotics, for example, by building these specialized little efflux pumps to physically pump the antibiotic out of the cell, that requires enormous biological resources and energy.
It's like having to build a huge, expensive firewall for your computer and dedicating half your processing power just to run the antivirus software.
That's a perfect analogy. Now, to resist the phage, the bacteria has to change its fundamental surface structure, those receptors the phage is trying to latch onto. To make that change and to maintain resistance to the phage, the bacterium often has to make a critical trade-off.
A compromise.
It has to give up, or at least significantly decrease, the energy it was dedicating to those efflux pumps and the other complex machinery it uses to resist antibiotics.
So they can't be superheroes on two fronts at the same time. They have to drop the modern chemical defense to maintain the ancient viral one.
And that is the leverage we gain. We can exploit this metabolic trade-off. We can trap them in a catch-22.
How does that work in practice?
So say we have a superbug that's resistant to drug A. We find a phage that targets it. When we apply the phage, the bacteria rapidly evolves to resist the phage, which in turn often makes it vulnerable to drug A again because it had to compromise its antibiotic defenses.
That is a genuinely sophisticated therapeutic strategy. It's not just about killing. It's about forcing the enemy into an evolutionary dead end. And we have a perfect, desperate, real-world case study that demonstrates this exact mechanism.
We do. And the case study is a profound example of phage therapy acting as a literal last resort. The patient was suffering from a devastating multi-drug-resistant infection that had, for all intents and purposes, consumed his chest cavity.
And the culprit was Pseudomonas aeruginosa. And for anyone who doesn't know, Pseudomonas aeruginosa is an absolute nightmare. It's one of the most feared hospital-acquired bacteria. It's opportunistic, it's naturally resistant to a huge number of antibiotics, and it's notorious for forming these sticky, protective biofilms.
Right. The source material notes this thing is so tough it can even survive most alcoholic hand gels. It's a true high-order superbug.
And conventional medicine had completely failed this patient over a period of years. He was out of options.
So the medical team decided to try the experimental treatment, leveraging that catch-22 strategy. They didn't just use phages alone.
That's the key part. They identified the right phage cocktail, a few thousand specific phages, and they inserted them directly into his chest cavity, together with the very antibiotics that the Pseudomonas was already officially listed as being immune to.
They were betting that the phages would force the bacteria to evolve in a predictable, beneficial way for the patient. The phages would create a selective pressure, forcing the Pseudomonas to compromise its antibiotic resistance just to survive the phage attack.
And the result?
The outcome was a stunning success. The combined assault was enough. The infections completely disappeared after just a few weeks.
Wow.
It wasn't just the phages killing the bacteria, it was the phages weakening the bacteria's chemical defense mechanisms, which then allowed the old, previously useless antibiotics to come in and finish the job. It was a victory achieved by understanding the evolutionary cost of defense.
That story is immensely hopeful.
Yeah.
But if this technology is so effective, why is it still experimental? Why aren't we just using phages widely to solve the superbug crisis right now? What are the big hurdles?
The hurdles are largely regulatory, logistical, and economic. And they're monumental because our entire medical infrastructure is built for the age of fixed chemicals, not living, evolving biology.
Let's start with the logistics of it. It's a form of personalized medicine, right? Antibiotics are kind of one size fits all. You take amoxicillin, it works against a general group of bacteria. Phages aren't like that.
Not at all. Remember, they're hyper-specialized. A phage that kills strain A of Pseudomonas might be completely useless against strain B. So if a patient comes in with a superbug infection, you can't just guess. You have to identify the exact bacterial strain. And then you need to find a perfectly matched phage or a cocktail of phages that can specifically destroy it.
Which means every hospital, or at least a central facility, needs a massive, constantly curated inventory of these things.
Precisely. You need what's often called a phage library. This is a physical living stock of tens of thousands of different characterized phage strains ready for immediate use. Building, maintaining, testing, and keeping that library standardized is an immense logistical and financial challenge. It's fundamentally different from just mass-producing a few fixed chemical pills.
The workflow is totally different. If I have a severe infection, the first step is a rapid diagnostic test to find the exact strain, then a search through the library, and then a custom cocktail is prepared and given to me.
Yeah.
That is a massive overhaul of hospital infrastructure.
It is. But the biggest bottleneck is still regulatory. Bodies like the FDA in the US or the EMA in Europe, they are designed to approve fixed chemical entities. When they approve a drug, they test its safety, its consistency, its efficacy. They expect the drug you get today to be identical to the drug you get 5 years from now.
And a living, evolving phage cocktail just completely breaks that model.
It shatters it. A phage is not static. If the bacteria evolves, the therapeutic phage must also evolve, or we have to swap it out for a new strain from the library. So how do you standardize a living drug that is constantly in motion? How do you conduct the traditional double-blind clinical trials when the treatment has to be personalized and constantly updated?
This system just isn't built for it.
The regulatory system really struggles to categorize and approve a treatment that is, by its very nature, personalized and constantly evolving.
It's a tragedy of timing, really. We have this perfect evolved solution right when we need it most. But the inertia of our own systems, which were all built around the failed chemical paradigm, is what's holding us back.
And that leads to the economic issue. Pharma companies are, understandably, reluctant to invest the billions needed for trials in a treatment model that doesn't fit the blockbuster drug approval process. Antibiotics are hugely profitable because they're widely applicable.
Right.
Phage therapy requires customization. That means smaller markets per strain, high testing costs, and very limited patentability because phages are natural, evolving organisms. The financial model is just very difficult to reconcile with the traditional profit-driven pharmaceutical business.
But you mentioned that things are starting to shift. The sheer urgency of the crisis must be driving some movement.
It is. The source material highlights that major clinical trials have started in recent years, including the largest phage clinical trial to date, which began back in 2016. And many countries, particularly in Eastern Europe, where phage therapy has a much longer historical legacy, have different frameworks that allow for compassionate or limited use.
So necessity is forcing change.
It is, but the process of building widespread, standardized approval for a living therapy is, by necessity, slow and very complex.
So the war against superbugs is accelerating, and the cavalry, the phages, are still waiting for full security clearance to be deployed widely. It really is a race against time.
Yeah.
But at least we now understand the winning strategy is already billions of years old.
We're finally learning the rules of the oldest game on Earth.
Okay, that brings us to the close of this deep dive. Let's try to synthesize this monumental shift. We've gone from an age of really chemical domination and complacency to an era of frightening vulnerability. The reign of antibiotics as our universal superweapon is definitively ending.
And we have to move from the age of that indiscriminate chemical carpet bombing to the age of biological precision targeting. It's a new methodology, and it's dictated by the ancient rules of evolution and predation that govern the entire microbial world.
And the central concept we're left with, the bizarre yet brilliant kernel of hope, is this. Injecting the single deadliest being on planet Earth, a specialized killer responsible for trillions of deaths every single day directly into our bodies that could save millions of human lives. It forces us to entirely redefine what we fear and what we should rely upon in the microscopic world.
What's deadly to bacteria is life-saving to us. The entity we once ignored as just a scientific curiosity is now our most promising ally against the existential threat of superbugs.
Before we wrap up, let's leave the listener with a final provocative thought, Something to mull over as they digest the scale of this microscopic war.
We've spent the last century trying to conquer bacteria chemically. Now we are choosing sides and actively participating in a microbial arms race that has been raging for billions of years. Our success depends not on stability, but on the continuous evolution and adaptability of our ally, the phage. So this raises a really fundamental question for all of medicine. What new dynamic frameworks in terms of research, regulation, personalized medical logistics, what must humanity invent and adopt, knowing that the battlefield, and therefore our most vital weapons, are constantly and rapidly shifting right underneath our feet?
That is the ultimate challenge, moving from a static view of medicine to one that is based entirely on embracing constant evolutionary change. Thank you for joining us on this deep dive into the world of bacteriophages. We hope you feel thoroughly informed, and perhaps just a little bit more in awe of the invisible machines living harmlessly on your eyelids.